Welcome to OpenSociety.wtf, a podcast where we explore how today's technology shapes our world, both in building a more open digital society and in creating its opposite. We talk to experts in biotech, Web3, and AI to find out how these innovations are impacting our daily lives. Today's episode features Professor Tae Seok Moon, who currently serves as a professor at the J. Craig Venter Institute in the synthetic biology group. This episode reflects on how individuals in closed societal environments have driven innovative research. In this case, we discuss a probiotic probe designed to detect gut microbiome conditions and also a global synthetic biology seminar series that supports not only young scientists, but also people like me in launching their careers. I want to extend my gratitude to Professor Moon for being my first guest on this podcast. I also want to acknowledge Professor Moon's student who, despite facing discrimination in a closed society, made significant contributions to the development of the COVID-19 mRNA vaccine, helping to save billions of lives. People trying to intersect blockchain and life sciences together.
My big honor to be your first guest.
Let's begin with your personal story.
And Korea now rich country, but
agreeing with your parents that you can do science instead of being a writer.
So it's all about collaboration, all about kind of combining multiple skill sets together.
So yeah, it's my honor to have you today as my first guest, actually. And
my big honor to be your first guest. So I don't know where to start. So should I start very beginning of my career?
Yeah, just anything you feel comfortable with, and any angle you feel good. Yeah.
Okay. So interestingly, when I was high school student, I wanted to become a writer or specifically poet. I want to write poem for my career. And then, as you can imagine, I'm from Korea, and Korea now rich country, but back and when I was young, I'm talking about elementary school student, we are not that rich country. Actually, we are poor country at the time. And when I mentioned I wanted to become a poet, my parents super worry about, because to them, writing or becoming writer is basically means hungry, not that much income. So they sort of convinced me to consider science, because at the time when I was the high school student, I was very good at also science as well. So I kind of compromised to make them happy in some sense. At the same time, I was convinced to have hobby. Writing poem as my, writing poem is my hobby, but doing the science for my career. And then one thing I wanted to do is at the time is I love chemistry. So I kind of said I want to, major in chemistry. And then my parents still believe at the time, oh, chemistry is a pure science. That means at the time, and means, though in Korea, pure science is also still means hungry. So not that much income. So, I compromise because they asked me to consider engineering. So I compromised and I chose one department in engineering that is actually basically the applied chemistry. So I, got into Seoul National University for my, college degree. And then I somehow found my passion in biology. And then, as you can imagine, biology is the science field. The main focus is to understand ourselves or living system. So I got into, I started thinking about what is human, what is life, and I thinking about that one for many, many years when I was the high school student and also when I was college student. And then to answer that question, I become very interested in biology. And then I took many, many courses from biology department, microbiology department, etc. And then I realized I really love biology at the time. So my career is not a straight line because I only took one biology course in high school and then I didn't take anyone. But now I'm doing the biology research. And then to make my skill set better, I did my master degree in biochemical engineering because I still in the engineering school at the time. And after that, I realized I still trained more than 60 years in college, including master degree. I'm basically, engineer, trained as an engineer. So I realized I believe I should work for company. So I joined company that's a biotech company, but we develop a lot of product and then we launch, 4 product to help patient, including some osteoarthritis patient and injection that makes your pain go away. And there are multiple other products we develop. And because of that, I promoted very quickly to manager position. And then I realized when I become manager, who coordinate preclinical trial research with 100 people. And I interact a lot of people at the time, mentoring the young employees in the company. And I found my passion for education or, helping other people grow their career. So, and then I realized I want to come back to academia and I start my PhD program 8 years later than other people. So my classmate is literally minimum 8 years younger than me or 10 years younger than me if somebody skipped their grade. And then I, done my PhD degree in metabolic engineering under the guidance of Kristalla Preder at MIT. And then after that, I joined the Chris Voigt lab. He is also leader in synthetic biology about the genetic circuit building and refactoring, etc. at UCSF. And then Chris Voigt actually moved to MIT. So I moved with him to MIT and then to finish up my postdoc. And then I start my position 2012 at Washington University. And here I just working with lots of great graduate student and undergraduate student and postdoc to develop my own program. So that's kind of my full journey up until today.
Yeah, your journey sounds like a grinding journey of finding yourself.
Not a straight line. This is basically exploring. It's a random movement, but finding new direction by accident or by fate in some sense. But I am here basically.
Yeah, so it's roughly at first you are kind of confronting or not confronting, you are agreeing with your parents that you can do science instead of being a writer. And then you move to chemistry, which requires a lot of logic. And then you discover biology. I think biology to me, it's very different from chemistry because it involves, skill-wise, involves a lot of memorization, but also, I guess you must see the beauty of biology in its expression of liveness, in its association. Do you see its association with poems and writings, and that's kind of resonating with your inner self or deeper self of your desire of being a writer? Do you see a connection there?
In some sense, yes. Let me put it this way. So when I was the high school student, college student, I constantly thinking about the question, why I am here. This is more like a philosophical question, I guess, and why people exist type of question. I constantly, ask that question. And then I try to find the solution or answers from physics and chemistry that does have answer, including interesting, I call it governing principles. Let me give one example. Recently, I published one paper about my several decades old thinking. I finally published on paper, I think last year, very recently. What I'm talking about is, for example, in physics, we have universal governing principle such as energy conservation, or in quantum mechanics, uncertainty principle, in chemistry, equilibrium, and also entropy increase. Those kind of governing equation or principle basically applicable to any single phenomena in the world or in the universe. And that fascinated me when I was a high school student. And then when I broadened up my horizon of knowledge in college, biology kind of fascinated me more because biology is very complex, but still there's no governing principle to me, because the only governing principle at the time I thinking about was the central dogma. DNA become the RNA, DNA replicate, and then also, protein made. But what else you could think about governing principle that basically applicable to any living system? And then another governing principle at the time I thought was the evolution. So it kind of, to me, I mean, this is something like very philosophical in somehow, thinking about the origin of life. And then that is so related to my original question, why I am here in this world and why human exists. So that's why, I kind of have connection between the poem or, art and the science, especially biology. And then probably because of that, I'm more attracted toward biology than other field, because I wanted to find new principle, governing principle in biology. So that is actually, I finally written about my idea. I identify now 7 governing principle in biology that's published in the Frontier journal recently. Yeah.
Can you share with us the 7 governing principles as you discover evolution?
Yeah. So I
using
didn't
your artistic
discover,
mind too. Yeah.
Yeah, I didn't discover the principle. I literally gave too many talks, seminars last 3 years. Total I counted that could be a little bit more than 180 presentation in the world. And then I asked the same question to other people. What is the governing principle that is unique in biology? And then I collect all the opinion from all the people, all the thought leader, synthetic biologists, physics people, chemistry people. And then finally, what I got was probably the 7 governing principle is, as I mentioned earlier, central dogma. That's probably nobody will argue against me. And the second one is probably evolution, because that's unique in biology. And then third one is biological robustness, because we talking about homeostasis, and that's very unique, in biology. And then of course regeneration, and then the fifth one is reproduction. Regeneration is more likely coming from bacteria becoming two bacteria, one bacterium become two bacteria, and then kind of also one connection between the form and regeneration. I love Eliot, the poet. You probably remember from your high school literature class, the April is the coolest month because the new living system coming out of the dead bodies, that or something like that. So same thing, regeneration is above the dead body, dead materials, new creature basically basically occur. And that is actually regeneration. Reproduction is basically we reproduce our offspring, or eukaryotic system reproduce, and that's the reproduction. And then sixth one is, I call it development, because the eukaryotic system develop. Also human develop from the baby to adult. And then the last one, this is a little bit controversial, but I call it causality. Causality means one thing. Yeah, causality means one thing lead to another thing, cause and effect. I believe the cause and effect is important thing because we constantly face moment of choice, and one choice lead to the other one, and then or one event in biological system lead to another one. So I call it that is causality. Causality is not unique in biology. Causality is everywhere, but I still wanted to include causality in the biological governing principle. In that way, make the total principle 7 rather than 6. So that's my 7 principle I gather from people.
As a biologist, do you feel pressured when you are proposing or not discovering, you are summarizing principles of biology? Do you feel pressured to reduce every principle to a single equation like a chemist or physicist does, such as
that's what I want to see. That's
Mm-hmm.
what I want to see, exactly. So if somebody summarize like quantum mechanical physicist done before, governing equation that govern everything in the universe, I believe that person will receive Nobel Prize in biology. But that is the not easy problem to tackle, I think.
Do you think it's even doable? Because to me, who never made it to a biological PhD, my experience was biology is messy, chaotic.
Yes.
And it always requires systematic thinking where there are just too many concepts and it's such a complex subject. Unlike any other disciplines, you can create a kind of logical map of things, but in biology is different. So do you think it's doable?
I hope so, but as you think, I also think biology is messy, and then we understand evolution a little bit, but not entirely. We understand completely. We understand genetic expression noise or randomness, but still, we could write the governing equation for some specific phenomena like gene expression. We have some governing equation that is published by Professor Parson, I believe, Johann Parson, many 20 years ago, more than 20 years ago. That only described how gene expression, noise could be described by a single equation. But if you ask me what is the governing equation that control or applicable to entire living system, probably my answer is probably we cannot find that one. Or if somebody believe in God, probably their answer might be God has the equation or God is equation. But that is the not scientific answer, I guess. So to me, I believe in Big Bang theory. Universe start with just Big Bang, and then after that, everything just based on causality, and then molecule formed that somehow lead to living system like virus and then bacteria later on, and then evolution control the entire process later on, and that's how I am here, and that's my governing theory, but it's difficult to prove, of course.
Yes, you mentioned your favorite poet is T.S. Eliot.
One of them.
One of them. So T.S.
Yeah.
Eliot is one of your one of your favorite poets. So who's your favorite biologist?
My favorite biologist, too many actually. I have too many, biologists. So it's hard to pick, but I don't want to go too far. I mean, but of course, I admire my advisors, two of them. The one, Crystal Prater and Chris Boy. Very different style, but amazing scientist and mentor. And then, I I I love all the, admire all the, scientists and engineer in synthetic biology, including, of course, Jim Collin and Michael Alloy. They literally start synthetic biology. And also my academic grandma and grandpa, Francis Arnold and Jay Kisling, and I admire them as well. And then, in metabolic engineering, Greg Stephanopoulos and also Sang-Hyuk Lee, Professor Sang-Hyuk Lee, and I admire those people's work. In engineering field, I also admire, let me see, Bob Langer. He's probably the most influential or famous engineer in history. He is also help Moderna develop COVID vaccine as well. So there are too many to list all of them, and I admire everyone's contribution to science and engineering.
Are there a common quality among them in terms of being a good biologist or an excellent biologist?
I mean, they constantly seeking for answers, and then always curious about new thing, and then always pioneer. So they are not staying, just one current status. They seeking for new innovation, and then find new thing. For example, Francis Arnold, a professor at Caltech, she is also Nobel Prize, winner, laureate, in, I think, chemistry because of the directed evolution. She was not biologist at all when she was I think the college student, but she changed her, field into biology, and then she start probably start to be interested in evolution and then invented sort of artificial evolution, but that is actually speed up evolution process by using in vitro, error-prone PCR, etc. And then because of that, she, got the Nobel Prize. But she never worry about new thing, always try new thing, and then innovative idea implemented. Because I mean, as I mentioned, if one person stay in their comfort zone, there should be no innovation in the world, and then we probably still do not have directed evolution at this moment. So that is something I want to say. Also, Jennifer Doudna, now everyone know in this biology field, Jennifer Doudna, because she basically discovered or developed CRISPR technology, and then before she developed new technology that enable genome engineering. CRISPR is only known to the community people who study CRISPR. But now she developed a new technology rather than staying in the science, but more engineering. I believe the combining some synthetic biology concept. Now she became so famous and then also got the Nobel Prize, I believe. So that is probably the quality of those people, not just stay in whatever comfort kind of area of their research, but kind of innovate or sometimes disrupt, the field or paradigm change in that way, kind of provide the vision to younger generation to follow. But that's probably not their quality, I believe.
For non-scientific people, what does it mean by being disruptive to a biological research? Do you mean that they have the ability to extract the phenomenon or the principle from a living body and being able to translate them in real life and kind of put it back to the living body and still make it livable there? Do you mean disruptive?
Are you asking what is my definition of disruptive?
Yeah.
To me, let me put it this way. So disruptive is something like you first challenge the current paradigm and then provide new solution or new concept about the current paradigm. So let me the kind of give some example. I just gave you directed evolution, so probably using the same example. So before directed evolution sort of suggested or proposed, people think evolution is long process, right? Million years of process, or at least the several decades of process by random mutation. That is what we believe entire time. But when Frances Arnold sees the evolution in a completely different way, she wanted to accelerate evolution by introduce high error rate. Because as you can imagine, people wanted to make the DNA as accurately as possible or synthesize as accurately as possible, but she think completely different way. I mean, this is now you may take for granted, but whenever somebody start new field for the first time, this is a slight difference but that's a 100% different direction because nobody tried that one. To do so, they need to be brave. They need to be innovative, and that is or even disruptive, kind of changing or challenging the current paradigm. And then she started to include, try to make the evolution in a much, much faster way, combined with a selection of new, better phenotype. So that's what she done. Synthetic biology is the same thing. And it's to me, biology before synthetic biology or before genetic engineering, biology is the field of observation. For example, you observe, how birds migrate. And then basically the conclusion is birds migrate during winter to warmer climate place. And that was biology. If you wanted to observe better, the only thing you kind of do in terms of manipulation is you basically cut the frog into half and then see inside. That is basically biology most of the time. But now synthetic biology, what synthetic biology, does is we wanted to understand biology by building some system, not necessarily big, but even small biosensor, and then try to understand how biosensor work or how genetic noise behave by building genetic circuit and then analyze that genetic circuit. And eventually, for example, John Craig-Venter Institute people even create or engineer new creature, but not necessarily this is a new creature. Basically, this is copying the existing creature, but basically reboot by using synthetic genome. And then now we have the ability to understand how those kind of replication and how minimal genome working by synthesizing entire genome and then making that survive. And then we could delete one gene at a time or make the minimal genome. And then we could now understand what is the minimum living component any organism could survive. So this is a completely different one. Before, observation-based science. Now, we now build to understand. So that, I believe, that's a disruption.
That's a process. Yeah, continue.
Yeah, process of disruption or the innovation. So that's what I meant by the disruption.
Yeah, so let's come back to your research, because you are also you're engineering your own life form to understand gut problems and understand probiotic bacteria. So talk about your research. And I think by thinking it in the opposite way, mean non-passive way, you are also disrupting the gut health field by
not yet
creating your not yet. You're in the process of creating a probiotic.
I wanted to.
Yeah. So I'm very interested.
Sure.
About
The concept is a disruptive, but I haven't implemented fully. So I'm not still that much innovative compared to the people I admire. So I'm not innovator yet. The conceptually, that's I would say still crazy idea, because I kind of start to implement some, but not fully implement. So I will give you some example of how I think regarding our health problem. So you mentioned gut problem. I interested in many other problems, but let me focus on gut problem today because we don't have enough time to cover everything. So people understand now, also realize many years ago, human, we think just human, but human is, total number of cell we have. I'm talking about human cell. Total number of cell of human cell is actually less than total number of bacterial cell we carry every day. So total number of bacterial cells is much bigger than human cell. That means I am not just human, I'm just human plus more bacterial cell I'm carrying every day or exchange every day, because if I travel, I cannot get new bacteria in my gut, in my skin, in my tongue, everywhere. And then I look at my gut, or because I have some, gut health issue, many years. And then I found very fascinating papers, several years ago, that is basically related to multiple disease. But let me focus on one disease for now, just to give example. So our gut, has many bacteria, but interestingly, this bacteria also metabolize some chemical in the gut, including some food we take. But at the same time, this bacteria have ability to metabolize, including degrade or synthesize neurochemicals. So people might be surprised because I'm talking about neurochemical found in your gut, but in fact, there are multiple occasions and evidence neurochemical actually exist in your gut. You may, because that's surprising fact to me, when I saw the paper about neurochemical found in your gut, because I always think neurochemical or neurotransmitter should be produced by my brain, not from here, the gut. And then when I look at more and more and papers, I realize there are not many, some papers actually discuss or even saying one of the famous neurochemicals or transmitter called serotonin. In fact, serotonin is produced by gut cells more than 90%. That means the majority of the neurochemical serotonin, in fact, produced by the gut cell rather than brain cell. That's kind of very interesting finding to me, because serotonin is a very important chemical that control your mood, happiness, etc. But basically your gut produces it. And then I realized, oh my, this is so fascinating. So I wanted to develop some sensor, biosensor, that basically your probiotic, that is actually, you probably take some yogurt sometimes, right?
Mm-hmm.
So yogurt contain probiotic. And then I was thinking about, what if I engineer probiotic that contain serotonin sensor, right? If I have serotonin sensor containing probiotic, and then you may take my yogurt, and then the one thing I want to do is I want to measure serotonin level without taking blood from your body, because taking blood is not fun. And then the only thing you need to do is take my yogurt, look at your, I'm sorry, I'm talking about poop in the morning. And then if the serotonin level is too high or too low, that's bad. bacteria produce, let's say, red pigment in response to the serotonin level because they have the sensor I engineer. That means today is bad day because your serotonin level is too high or too low. So you don't need to you should not do anything. Just stay at home, do nothing. Because today is the unhappy day.
Mm-hmm.
Why, that's the case? I mean, tomorrow maybe your serotonin is just right between whatever range, let me say 30 to 100. And then bacteria now produce green pigment. And then your poop color will be green. And today is a happy day, so you do whatever you want to do. But that's one idea. But why we stay there? We want to go one step further. One difference between the computer and bacteria is bacteria do something in response to input, like making us happy or cure the disease. The idea is something like this. Let's say a chemical, or in this case, serotonin level is the 30 to 100 is the happy zone or happy level. If a bacteria see serotonin level is too high, bacteria start to produce enzyme that basically degrade serotonin because those kind of enzyme already identified by we already identify those enzymes. If a serotonin level is too low, bacteria start to produce serotonin, and then your level of serotonin will be between 30 and 100. And I already have company. That company will focus on development of those kind of probiotic. And I already have the commercial punchline. And that is basically, do you want to be happy? Take my yogurt and you will be always happy. That's a crazy dream, but I'm gonna implement. But that's not necessarily only the serotonin thing. If some chemical should be a certain range, we can use the same concept using the biosensor in the probiotic, and then we could use the degradation enzyme or synthesis enzyme in response to the signal probiotic getting, and then we can make the level constant range. In that way, we could prevent any disease or even cure some disease based on that technology. So that's my crazy one, but we still in the process of developing sensor rather than the implementing the second part that is basically controlling the enzyme.
Right. So, what's the challenge of developing a sensor? Is it because no one has done it before, or is it because we haven't got the tool right, haven't got the right AI to accelerate development? What's the challenge here?
Challenge up until now was we didn't have many sensor to use. So for example, we in fact recently developed a neurochemical sensor in probiotic, bacteria. And that was the first example we developed sensor that detecting neurochemical. The keyword here is the specifically. There are some sensors that detect, for example, neurochemicals, including dopamine, serotonin, or some other neurochemical, etc. But they respond to many different neurochemical non-specifically because their structure is very similar. So we actually use computational algorithm like Rosetta, or many people heard about AlphaFold. Use those kind of algorithm, and then we kind of use the computational modeling in terms of the chemical protein docking simulation. And then we found the some mutation, if we introduce, we could kind of make this one more specific to this only one chemical. Simple idea is, I mean, that not necessarily, this is to explain for the general public. So let's say this is the pocket for the sensor, and then you have the pockets too big, and everyone just kind of approach here, and then kind of detect by this sensor protein. But if you make that is just small enough, and only the smallest molecule could get into the active site or the binding site, and then you could kind of detect only one. So that's basic concept. But you could use them, hydrogen bonding interaction, hydrophobic interaction. In that way, you kind of change the protein just right for the one molecule. We can make that. One challenge before was we actually rely on directed evolution by the Francis Arnold, creative. But that we need to screen minimum 10 to the 7 or 8 different variant of protein. And then the screening is actually very challenging. But now we have the AI or AlphaFold or Rosetta. We could now use computational simulation. In that way, eliminate some bad protein structure and only down select, let's say 100. Actually, we screen only 100 based on computational modeling. And then basically we do so-called saturation mutagenesis. That's one of the directive evolution kind of technology. And then now we screen only 100, and then we found many good sensor only detect one chemical, but not others. But that is the sort of now solved problem, but still we need to develop more sensor. But another problem to achieve that, I call it dynamic control. This is kind of temperature control in the room. Temperature too high, you make the air conditioner on, go down. Temperature is too low, heater basically on, temperature go up. But temperature control in the room happen very quickly, right? In the order of some minute. But you're talking about sensor, depending on the application. Let's say you want to maintain the serotonin level around 30 and 100, your sensor and enzyme expression, everything should be quickly happen within the fluctuating concentration time range. But our gut is very complex, constantly changing concentration. Also, when you eat something, you may have the different chemical composition. When you relax, there are different chemical composition. When you kind of study different chemical composition, etc., how we gonna make the probiotic quickly respond to those kind of fluctuating chemical concentration, and then make those kind of concentration in the same range I just described. So that's some example of the challenge we currently facing. And then the other challenge would be your composition will be different. Entire composition of chemical in your gut different from me. Also today different from tomorrow, and then in the morning different from evening. How to make the probiotic sort of generalizably applicable regardless of this kind of difference. So there are many challenges we need to address. So that actually make me more excited, but at the same time, I'm not still innovator, conceptually innovative, but we haven't implement entire spectrum of the research fully, but we just began to address the first part, that's basically sensor development.
Yeah, I think it's already a hurdle to design an application in the biological field because, as you mentioned, it's so complex. Everyone has different conditions.
Mhm.
and that's, you're talking about the macroscopic level. People are different.
Mhm.
And you're also talking about at the protein level.
Yeah.
You need to screen like 100 proteins, maybe not 100, in like in vitro or something. Maybe 1,000, 10,000 proteins in the
Mhm.
computer every day to
Mhm.
screen 100.
Yeah.
I think that's already, yeah, I think the most difficult part about biology is just the variables. It's how do you get the life right to the precision where you want to just dock a single serotonin or something. I think it's very challenging this way.
Yeah, but that's not, that's, I believe that's doable, because think about in the past, we
Yeah.
we we didn't have antibiotics, many years ago, but we now have the antibiotics. We didn't have the vaccine, but now we have vaccine. So technology advanced, and then our lifespan increased significantly because of vaccine, because of antibiotics. So the question I just kind of propose right now is crazy at this moment.
Mhm.
But the considering the progress we just saw last centuries or before, I believe those kind of dream could be implemented, not necessarily in my lifetime, but I giving this kind of vision to young people, basically hoping you young people solve the problem for my daughter or for my granddaughter or grandson in the future.
Do you
That's
have
what I.
any advice for young people who are undertaking biology as a career and wanting to use it to help human to live longer? Because from my experience, I did biochemistry in undergraduate, and I didn't take any other subjects in my university. So I
Uh-huh.
found it really difficult to be a, a biochemist who is only equipped with like biology. Do
Hmm.
you have an advice for like young biology students who really
Sure,
want to make a change, but they struggle?
sure. So the one thing I want to mention that's relevant to what you just said, uh, nowadays, science field is very interdisciplinary.
Hmm.
If you kind of only limit yourself to biological, subject or the class, your horizon never become bigger. So my suggestion is, or recommendation is, try to be open to other knowledge, including
Hmm.
physics and chemistry and even computer science or AI. Nowadays, everyone interested in AI, so I don't need to worry about that part. But so think about to make biology easier and possible, or advanced. Now we need those kind of concepts from physics and chemistry and other field as well. And then, but the other thing I want to mention is, you said you sort of struggle in some sense, but don't worry about those kind of struggle, because
Hmm.
you are young, you learn from failure, and I always tell young people, don't afraid about being, being, I mean, don't afraid, you being failed, whatever, your degree or your project or what you try. Because when you fail, and then if you recover, you learn much more than people ever fail. because you are still young, you could recover for sure if you try more. And then some people I see, they worry about failure so much, and then they never try something new. Just kind of go the same route, just kind of simple, comfortable life. That doesn't lead to innovation and something great. I mean, if you choose that life, that's fine. I mean, that is another life. You just kind of have normal, ordinary, average life. That's another life. But if you wanted to do something meaningful, that is kind of has big impact, never to be, never worry about things. I mean, just try and then dream high. And then one day, you will realize you already become a leader you never thought about. So that's one thing I want to tell every young student and postdoc in biology field or even other field, because that is what I, learn from multiple failures and multiple, tries. And then that's, what I want to say. I wish I knew, I mean, those kind of things earlier, but now I realize after 50 years of my life. So yeah, just dream high. In one sentence, dream high. Never worry about things. Just work, try hard, and then never give up. That's one sentence, my advice.
Yeah, I think most people when they were young, I did, but I'm still young. So several years ago, I still fear about time. Like when people don't know what to do, they have uncertainty, so they fear about time. Maybe it's forgetting the time component. Just try it, making you, and forgetting the time component, accepting it's difficult, it's fine. I think that's gonna make a difference. So
Yeah.
you talk about like being versatile in knowledge and pursue different knowledge in order to do something in biology. So I think you deal with a lot of genetic circuits every day. Do you think people with a computer science background, they will do a lot better in biology than people who are purely trained as a biologist? Because biology nowadays is getting more complex in terms of its concepts. As you know, genetic circuits. To me, it's a lot like logic gates, and maybe it's people with computer science background, they get it easily. Do you think that's true?
So you are asking, now do I believe computer science and biology could marry together?
Or people with a computer science mindset or a more mathematical mindset would do better in biology if they have
No, let me
a
please say,
passion.
not
Yeah.
better, but they could do biology easily, of course. So let me give one example. So
Yeah.
I actually thought, interestingly, this coincidence. Tomorrow, my global seminar series, weekly seminar series called SynBis. The SynBis seminar speaker will be Dr. Lee at the UT Southwestern. He used to be a biologist, but now changed his career completely computer scientist or programmer. Okay. Interestingly, his now current advisor is actually completely programmer, computer scientist, just programming. Nothing he done before, any experiment, biology experiment, never. But what they are doing is, so one of them is a completely hardcore, biologist talking about something you just learn from the textbook in biology. The other guy is basically completely computer programmer, but they met, and then now they are doing is programming biology. I was so fascinated by, I met them when I gave the seminar in that university, I think last year, or I don't remember exactly. So I gave a talk over there, and then I heard about their research. Their research is basically entire human, for example, human body. They wanted to make computer code describe entire human body. So, for example, what they want to achieve, this is amazing. I mean, I still kind of want them to succeed. What they want to do is programming entire body in that way. If you, for example, simulate, let's say, one drug injection, some new drug injection, what would be the side effect? And the entire thing is done by computer simulation. That's their dream. And then what kind would that drug will cure whatever disease in the body? So basically, that's amazingly, basically every single transcription, translation, chemical transport, metabolism, everything, basically they write code using computer program language and then basically simulate, and that's what they want to do. There are many companies, purely computer scientists, some biologists, they wanted to do similar thing, but what they described, the UT Southwestern, that's the probably most extreme or most potentially disruptive idea. So to answer your question is, my answer to your question is, yes, absolutely. Computer scientists could do biology. But as I mentioned earlier, nowadays, any field is very interdisciplinary. And then one person cannot solve any problem because we need to collaborate. So this example is great example because computer scientists met the biologists, and then they are now talking about making program or computer code describing entire human body.
I think they are pretty lucky because they kind of bypass the barrier of communicating jargons.
Yeah.
I think they're at the point where they trust each other. They know what they're talking about.
Yeah.
They're translating different languages all at the same time without a lot of hurdles. That's a very lucky combination, I think.
Yeah. But many people I know, I mean, in fact, computational biologists, and then start to do some experiment in biology. Some people just done experiment like me, entire my career from master degree to, I would say, PhD. I done only the experiment. Of course, collaborate with the computational biologist to predict the protein, as I mentioned earlier. And I screen becoming the robot, pipetting every day, screening 20,000 different colony by hand. But I collaborate with the computer scientists. My advisor, Chris Boyd, used to be computational biologist, just making the program to predict, error-prone, not error-prone PCR, basically the directed evolution using some, it's called schema, I believe. That's a recombination method. But now he working with student and postdoc to incorporate lots of experimental component. And I became also using computer simulation or AI, machine learning nowadays I just use lots of computer program algorithm. Also, I use the MATLAB to analyze genetic circuit myself. So it's all about collaboration, all about kind of combining multiple skill set together.
Yeah, I think in the US, the resources is abundant, and kind of labs can they collaborate and they make things happen. But in some areas in the world, maybe a lab doesn't necessarily have like a robotic equipment. They have to do everything by hand. So do you think this kind of imbalance of resources distribution, once scarcity, once abundance, they're gonna making the other labs obsolete?
Not necessarily. Let me give one example. Actually, I met yesterday one iGEM team. iGEM, the International Genetically Engineered machine competition. That's a premier synthetic biology competition. I just kind of explain that one for the general audience. I met one team yesterday virtually because they wanted to thank me. That team is from Africa. They don't have any resources. The only thing they had was passion to do synthetic biology research. And their journey is amazing. They approached me to give some advice, and I agreed, and then I helped them last year. And then, of course, their passion led them to reach out to other people, including some company and also some organization. And eventually they financially supported by those kind of companies and organization. And then even, I believe, attended the Paris Jamboree. And obviously, their lab situation is worse, much worse than university in US and or UK or European country. But their passion basically achieved significant milestone. And based on that experience, they also even start a company. So I know they have more challenges than people in US and UK or European country. But if you have passion, you could achieve amazing thing. And then I saw myself by my high eyes, they achieved, and then they said they continue to pursue to make their dream possible, and then eventually helping people in Africa to cure whatever disease or detecting some disease in the environment, basically. So that's what they want to do. So bottom line is, the most important thing is your passion. Never give up, as I mentioned earlier. Just continue to work. Of course, work hard, and then one day you will achieve, whatever your goal. That's what I want to say.
Okay. Yeah, I think scarcity really makes people know clearly what they want, and it's about directed evolution, right? The more challenges you have, the more regeneration you'll have, and the more evolved you become in a short amount of time. So I really respect their passion and their action of making things happen, and also you're helping them with this. It's really good, I think. So because this podcast also we have the aim of understanding data storage problems in biological labs. So, but for me, because I didn't pursue a PhD, so I'm not very sure deeply involved in this IT problems in your biological lab. So how much do you know about like data storage problems and solutions in your lab, and how much data kind of you produce every year? I guess it's significantly like amount of data you produce from screening and isolation, and also
So let me put my my perspective. So I am currently working for 9 journals as an editor. So that means I reading a lot of papers. I review a lot of papers. Also, many of my colleagues really only focus on data storage in DNA or any biological system. So I'm familiar with that concept. We in my lab haven't done any project related to data storage, but we actually working on the memory device. We call it memory device. So for example, if I talking about gut problem, and then there should be some way to retrieve or see what is the result, whether you have the disease or not. Earlier example I gave you basic color, right? You see the color, and but if bacteria do not see the neurochemical in the poop, your color probably only exists in your gut, but not in the poop. So actually we develop memory device. The color stay as, even after the bacteria come out of your body, still color stay. Or we can kind of record that output in the DNA. Actually, we actually use the DNA, recombination. In that way, kind of DNA kind of after we got the signal, DNA basically kind of permanently change, and then we see whether some disease kind of detected in the gut or not when we analyze the bacteria in the poop. So we done some storage somehow, but that's not storage you're talking about. You're talking about gigantic amount of data stored in the DNA. And then, but I know, the concept very well because of my colleagues and because of the literature I read, last, many, more than decades, basically. To answer your question, I believe the storage, information storage in data, information storage in DNA is, I believe, the huge potential in the future. And then that actually technology actually currently exists. So there are multiple papers published regarding data storage. And actually recently I published one paper, review paper. I talk about the data storage in DNA. So that's why I'm kind of familiar with that one. But based on my reading, my literature search, and my conversation with other people, that is necessary. Storing data in DNA is necessary. Let me give my personal experience. I'm in the school, and when I was in college, that is basically early 1990. So I got my bachelor degree 1998. I bought my personal computer during the college year. My first personal computer. Actually, I have the one computer when I was young, but that is bought by my parents. But I bought my personal computer for the first time by saving money, and I was delighted to have my computer has 2 giga or 1 giga. I don't remember, 1 giga hard drive, and then half of the drive filled with computer games that's provided by the someone who sold that computer to me. I was so delighted. Too many games. I even play all of that. I couldn't finish all of that. But I'm talking about 1 giga hard drive storage.
Mhm.
If you have computer right now with 1 giga hard drive, you cannot run any program or even window. You cannot run the program at this moment, I believe. Because we are now talking about, I believe, 500 giga or even whatever terabyte hard drive. But do you feel your computer hard drive is big enough for your computer? Probably not. My computer
No.
right now, even 500 gigabyte, I already store all the program and files, not necessarily the data. Data is stored in the additional hard drive. So I constantly feel like my hard drive is not sufficiently big enough to store the data. But that's not including the sequencing data and all the data generated every day that's stored in the bigger hard drive and bigger storage. So that means we need some new storage method, and that might be the DNA. Good thing about DNA is you could store amazingly large amount of data in DNA, but in a very small space, because you could just store that in very small space, including bacteria or just tube. One challenge would be how to make the storage as accurate as possible, because synthesis technology still generate more errors compared to computer hard drive, right? So storage, the most important thing is accuracy, but we need to deal with that challenges. Second problem is you don't want to wait to retrieve your data for
Yes.
1 days, right? But now DNA storage technology, you need to do sequencing again to retrieve the whatever stored data. And now, sequencing become faster and cheaper, but still you need to wait some time. So those challenges should be addressed. But we watch many sci-fi movies, and one day that might be possible. That's my answer to your question.
Yes. So just out of curiosity, like how much data do your lab produce every year? How many?
I never dared to calculate, because they constantly asking me to, we need to have more hard drive.
Mhm.
So my computer, my personal computer, I constantly back up my files and data. I even do not, store the sequencing data at all. Just, because that delete every, So we have some separate hard drive in the lab. We have the multiple of them. In that way, we have the backup. And then we also have, every universe has, I believe, center space. You could kind of store the data into the center, or some, there are many other ways, including simple thing is a box drive, cloud space. You kind of store those kind of data over there as well as a backup. Yeah,
Right.
but
So
still, one problem is if you store data in the DNA, that might be stored in long term, but in terms of retrieving, not that much convenient. Even if I want to go to the box folder, I kind of realize, oh, this is kind of one step further than my computer hard drive, right? So I try to put everything in my hard drive, in my computer, rather than putting into the box folder, because I need to log in to that box folder as well.
right. So usually universities they do have super data centers to store data.
Yeah,
Yes, the
also,
interaction. Yeah.
yeah. Although sequencing data stored in the gigantic, storage, device, some centralized one. So if because we do a lot of sequencing, if those some institute has the sequencing facility, they maintain their own storage device somewhere.
Is there a need to retrieve the sequencing data every day, like every hour or something? Or there a distinction between like cold storage, some storage you don't want to retrieve often, and some like kind of hot storage you want to retrieve or interact with the data every hour or so?
So I guess, I mean, there are multiple storage space. I mean,
Mhm.
probably as soon as you have the sequencing, I guess that
Yeah.
data probably stored in the whatever computer attached to sequencer, and then they kind of
Mhm.
probably receive, after a few days later. Uh, I guess, I mean, they store those things probably temporarily in that space, and then probably move that to the main bigger space, I guess. But depending on the university, or depending on the sequencing facility, they have probably different uh, rules or policy. So I honestly don't know how every other institute or facility could doing so. But basically, they have always a backup storage place that's a much bigger capacity, and then the
Mhm.
probably local computer also store some data probably on site, I guess.
Yes. Yes, I think you answered my questions really
Mhm,
well.
mhm.
Yeah, so you envision a future where every data you store in your lab, it's stored in DNA and can be retrieved
Hopefully,
easily. Yeah.
yeah.
Yeah, that's a very exciting future to envision, I think.
Yeah.
So let's back to like some consensus problems in academia.
Mhm,
Because I remember last time I met you and you were having problems we talked about before we started this episode. So you mentioned about some human problems that's kind of environmental problems you cannot solve. So do you think although it's like environmental problem, do you think it's a result of coordination problem within the academic department, or some kind of other problems within like the system that we are in?
sure. So, let me give my perspective. So,
Mhm.
unfortunately, uh, university used to be non-profit organization. I said
Mhm.
used to, and because the university start for the higher education, and then to pursue knowledge and discovery. But now, especially the US university, unfortunately, becoming profit organization. I understand in some sense, because without money, they cannot operate. But now they focus more on money generation than uh, education in some sense. Let
Mhm.
me give some, example of my conversation with my university leadership people. Whenever I wanted to do something important for the education of my student and in postdoc, or anything including my seminar series, that's basically free education distribution. But whenever I ask some, for example, could I get some support for the Zoom webinar license? That's only less than $1,000 per year. And then the answer is basically, what is the return on investment?
Mm.
That's a absolutely not acceptable answer to my question, because if we talking about return on investment, we are talking about that's the company, not the non-profit organization. If you insist to ask what is the return on investment, my answer is the return should be generating next leaders, or generating better leaders who could make this world better. That should be return. But what they ask, what is return on investment, how much money I'm generating by doing SynBio seminar series, or how much money I'm generating if university invests a certain amount of money. So that is the current problem. University becoming more profit organization than non-profit. And in some sense, I understand, but we need to change our mindset, because our goal as a professor or university people, our goal is basically generating future leaders, not generating money. So that means we need to invest more money to make their education better. But basically, university only care about now money and reputation, because reputation means more generation of money by donation or by tuition gathering. So how can I solve that problem? I try, more radical or more proactive, more rapid approach, but I believe I fail, because that's against what they want to see. So now I realize probably the most productive way to solve that problem is helping young people, including the people in Africa who passionate about change or passionate about solving global problem, or talking to you. You care about future, or care about technology development, care about distributing ideas to other people to make the better world, and then helping all the people who talk in my seminar series, especially young faculty or postdoc, because they believe in one thing: they could change the culture or technology or world by developing some new technology, or by discovering new thing in the world, or in biology or synthetic biology. If I help those people, it takes more time than doing something radical at this moment. I believe helping you guys, young people, you will become a better leader, let's say 20 years later. And I believe by that time, you implement better policy, better thing than our current leaders do. I believe that is probably the best way to solve this kind of cultural problem in academia, or toxic culture in academia. Of course, there are many great leaders in the world who care about people or diversity, equity, and inclusion, but still many people in leadership people wanted to just maintain their power, only maintain their power rather than nurture young people in the academia. So somebody should do something, and then that happened to be me, or some other colleague who think the same thing as I did, or as I do. So that's what I want to do in the future, or I continue to do so.
So you envision the future where the education led by current young people, and it's maybe less degree of top-down control of funding and directions, more bottom-up efforts. And
I believe it's bottom-up.
Yeah. So there's a thing in like the blockchain or Web3 industry called peer-to-peer funding, or there's a project called VitaDAO that led this endeavor where where scientists or labs or projects, they can in the science domain, they can propose their proposals on a marketplace, and whoever gets more votes, they will get funded.
Right.
And everything, the funding and the work will be recorded in the decentralized ledger technology, which is immutable and everyone can see your work, and it's kind of proof work, and no one can change it. I think maybe that's driving more peer-to-peer or bottom-up efforts in life sciences area, and maybe more people can get out of it instead of relying on universities.
So I believe there are many DAO, including Beta DAO, and there are many DAO kind of activities. That's basically concept is a decentralized, funding or decentralized kind of decision process. And I welcome that kind of activity. I kind of supporting many other DAO as well. So, and then there could be potentially disruptive approach to the research or to develop new technology. So I admire people working in that DAO system, because that is basically decentralized, and then decision is made by everybody rather than top down.
Yeah.
So hopefully that become bigger and bigger in the future, and then that's why I'm more optimistic, even though we have currently many problems in the world or in academia, because young people believe in new approach, including DAO system and some other thing. So that's why I rely on you, young people, and then you guys changing the culture and world, of course, together.
So were you a pessimist before in 2021 when I met you for the first time, before you kind of rank us on with yourself?
When I met you 2021, I became an optimist. If you ask the same question 2020 or before 2020, I was hopeless and pessimist because I didn't see, because at that time I was so sick. I literally dying. My dying period actually caused by discrimination and harassment by the leadership people based on race, gender, nationality, etc., or belief. So my almost 4 years of dying period end miraculously because one of my students who also discriminated by the leadership people in the university somehow endure and never give up, and then join the Pfizer and then develop COVID vaccine and became a world hero after enduring entire thing. And after I see that, I realize life is too short to regret or blame. And I need to move on. And somehow after realizing life is too short or too long, depending on how you think, how you see the life, how you see the career. And then I completely changed my perspective on life. And of course, I used to be a selfish professor, only care about my own student, my own reputation, my own research, constantly worry about being scooped, constantly worrying about getting the publication, getting funding. But after that 4 years of dying years, and then completely changed perspective, and then that lead to my miraculous recovery. And then when I met you, at the time I already sort of recovered from all the difficult time. And then I became the optimistic. The reason I become optimistic, I'm now more optimistic than 2021 when I met you, or 22 when I met you. Probably I met you 2020, because 21 I gave a lot of talk, but virtually, because at the time still pandemic. So when I met you 2022, I think summer, when I gave talk in UCL, at the time I'm very much optimistic because I met a lot of people, especially young people, who still have many problems, including, simple problem like you recently broke up with your girlfriend or boyfriend, or problem like your experiment never work. Your experiment for 6 months never work. You fail exam, or at the time many people unfortunately pass away because of pandemic. So there are many mental stress. There are many personal problem, including war, disease, pandemic, simple life problem like relationship between boyfriend and girlfriend, divorce, whatever problem you may have. But I became optimistic. I recover miraculously from 4 years of dying years. And then I saw many people, I met a lot of people by traveling more than 150 days or 60 days a year, meeting 1,000 or 10,000 of people. I realized everyone has personal problem, but they deal with. But many young people at least passionate about solving problem, including climate problem, medicine problem, health problem, sustainable production, agricultural problem, and people in Africa still wanted to improve their life, even helping other people. And then all the young people basically gave me strength and then optimism or hope. Because that hope, I lost 4 years, but now I hope more than ever. And because of them, I'm happiest because one day you will make better world for my daughter. And I optimistic, yes, I'm optimistic for sure. Because
Thank
of
you
you,
so much. Yeah,
of you.
young people. Yeah.
Yeah.
So
Oh,
I guess there must be a moment where you started, okay, I need to go out and travel and see the bright side of the world. What was the
sure.
moment you
So the moment is basically, since 2017, that discrimination happened to my student who became the world hero. And I literally could not speak up at that time because I was untenured professor. So I decided to become a coward. And then every single day I regret. What if I speak up? But probably at the time, if I speak up, I probably fired from this university. Because as I mentioned, university became profit organization. If I speak up, that basically damage their reputation. And then, firing one professor, untenured professor is easy thing to do. So I became a coward, but entire 4 years, I regret and blame people. But the moment was, I saw my student in the news. I think one of the African news in the internet when I was waiting for my last day. Literally, I waiting for my last day, 2020, when everyone suffered from COVID. I didn't care about COVID at all because anyway, I thought I probably died that year, 2020. But when I saw the news in the African whatever news, my student became a hero by developing the first COVID vaccine at Pfizer, who suffered from discrimination and harassment entire his time in US, but he overcome that difficulty and challenges and then never give up and then dream high. and achieved his dream. To give some idea about his difficulty, his home in Africa at the time even didn't have electricity. His mom suffered from cancer. His salary is not that high because US student, graduate student salary is not that high, but he still saved money and sent money to his parents or family to support his family in Africa. And then after all that trouble and difficulty and challenge, he became a world hero and then just show up in the news article. And then later on, he became a world hero, of course. And that moment, I realized my problem is just nothing compared to people suffering from war, disease, hunger. And I completely, changed my perspective because why I just complaining or regret. And then after that, I miraculously recover by reducing and completely stop taking all the medicine I had because I met a lot of probably 10 specialists I met during 2020 or before.
Mhm.
And after that, my health gain become better. I used to have 52 kilogram with the 180 centimeter, very skinny during that dying years. And then now I gain 30 kilogram over 1.5 years. I'm happiest man because I gained 30 kilogram after 1 year, 1.5 years, because I now enjoy my life, gain my appetite back, eating too much, I guess, to enjoy my life.
Yeah, you changed a lot in a very good way since the last time I met you.
Yeah.
Last time I think you were recovering, but you still have this grief of emotions. And
No,
you obviously gained a lot of weight.
2022, I was happiest. Like,
Yeah, but you were skinny.
no,
a bit.
2022, no, I gained weight. At the time, I skinny, but I gained weight a lot.
Yeah.
2022, I was gaining weight, but 2020, I was really, really skinny. I'm talking about 52 kilogram with the 180 centimeter. So can you imagine how? And then I even only eat 1/3 of my daughter eating at the time. But now
Right.
my daughter eat more probably now, but still I eating a lot. So yeah.
Yeah, I can imagine. It's just very hard to imagine like those racism and harassment still happen in like higher education, in a department where PhD students they live and work.
You know what? That is the century-old problem in America, unfortunately.
Mhm.
There are still, unfortunately, this nation is democratic nation, but unfortunately, the history of discrimination and harassment just prevail in some part of the country. Not all, but some part of country almost every day. So we need to deal with or solve the problem.
Yeah, I think you came to America when you were, is it after your manager period or is
Yes.
it before?
I basically became the manager, and then I realized my passion for education, and then I attended the MIT, as my first American experience. Uh, I mean, Boston is better, more liberal, and San Francisco is much more liberal than Midwest city
Mhm.
I currently in. even my daughter sort of discriminated by some young boys and other people, but that, minority should deal with anyway. So my student overcome, even he's the completely black guy, and I overcame as well. So hopefully a lot of people, minority people, potentially overcome that challenges. And also there are prevailing problem in science and engineering. Female is not that much recognized by the community, and that problem also need to be solved. Yeah, but I hope, young people now more aware of diversity, equity, and inclusion problem than the older people. So one day, I believe that problem will be solved by the young people caring more about the called DEI, diversity, equity, and inclusion. So that's why I'm optimistic than ever.
So to kind of finish this episode, do you have one sentence you want to speak to your student back then who contributed to the first
My student.
COVID vaccine? Yes. Do you have one sentence to tell him?
You know what? My student is super busy now. He promoted twice. And then now he's very busy. He attended recently US Africa, whatever National Academy meeting. That's the National Academy, in US is one of the prestigious kind of organization. He traveled, many places. In fact, I invited vice president of Pfizer and him to my house, and we had the coffee or tea, for 2 hours, I believe. So he's very busy. He continued to produce great product to help many patients because his passion is probably related to his mom suffering from cancer. Her mom and his mom still, suffering from cancer, I believe, but now still, she's alive. Fortunately, I believe he recently, visited, his mom in Africa. So, I'm glad. One sentence thing to say to him. Let me see. Okay, that is probably the one. So he of course thanked me a lot. Many people in the world who I help by meeting, giving advice, they thank me a lot. Including the African, IGM team members yesterday. But one thing I want to tell him and all other people I helped, I'm helping them not because I want something from them. I helping them or helping my student to see better world. So if I want to say one thing to him, my student, remember all the teaching or lesson I gave to him. Remember that. And rather than thanking me, giving the same thing, same hope, same contribution to help other people in the world who need more help. And that's one thing I want to. In that way, we create better world by helping other people who really need help. So that's one thing I want to tell him.
Okay. Thank you so much, Professor Moon. The very
Sure.
productive 2 hour, I think we had.
Sure.
Yeah, and thank you so much for your input. I really like it.
And it's my honor to be this part of the episode, also the first guest of this episode. So good luck with your episode, and I'm happy to interact more and then I want you become very famous, journalist or whatever. And then if I see you, 10 years later on TV, I want to proudly talk to my wife. See, my wife keep thinking about why you're talking to people you don't know well. And my answer to my wife is, you never know, those people, including Sunny, become very famous journalists, helping a lot of people in the world. And then I could proudly talk to my wife, say, I was right, because Sunny become somebody very influential in the future. And then people I help, I hope those people become next Bill Gates. In that way, helping a lot of people in the world. And that's all I want to see.
Yeah, you are very kind.
No, I
I wish all the success with the probiotic design.
I just want to help people in that way. A lot of problems solved for me and for my daughter, and that's it.
Yeah, thank you so much.
Okay, all right. Keep in touch.
All right, thank you so much, Professor Moon.
Okay, bye bye.
Good day. Bye bye.